What specific problem does the LazyLLM method aim to solve related to the inference of large language models, particularly in the context of time to first token, TTFT?
The LazyLLM method specifically aims to address the inefficiencies associated with the time to first token, TTFT, during the pre-filling stage of large language model, LLM inference. It recognizes that the computation of the full key value, KV, cache for all prompt tokens can be slow, particularly for long prompts, as the attention computation grows quadratically with the number of tokens. LazyLLM improves TTFT by selectively computing the KV for only the tokens deemed important for predicting the next token, thereby deferring the computation of less relevant tokens to later steps. This dynamic token pruning approach allows the model to adaptively choose which tokens to compute at each generation step, significantly reducing unnecessary computations while maintaining accuracy. Additionally, the introduction of an aux cache ensures that previously pruned tokens can be efficiently revived without redundant calculations, thus optimizing the overall inference speed.
How does the proposed LazyLLM algorithm work? Please illustrate the steps involved in its process, including details about token pruning and the role of the aux cache.
The proposed LazyLLM algorithm operates by selectively computing the key value, KV, cache for only the important tokens needed for generating the next token, thereby optimizing the time to first token, TTFT. The process begins with the full context, where LazyLLM progressively prunes tokens based on their importance, determined by the attention scores from the previous transformer layer. This dynamic token pruning allows the model to choose different subsets of tokens at each generation step, which is crucial for maintaining performance. To manage the potential loss of information from pruned tokens, LazyLLM employs an aux cache that stores the hidden states of these pruned tokens, enabling their retrieval without recomputing them through earlier layers. This caching mechanism ensures that each token is computed at most once, thus preventing any increase in runtime compared to the baseline while allowing for efficient revival of pruned tokens when necessary.
What empirical evidence or experimental design did the authors use to validate the effectiveness of LazyLLM, and what specific metrics were reported to demonstrate its advantages?
The authors validated the effectiveness of LazyLLM through empirical experiments conducted on two large language models, Llama 2 and XGen, using the Long Bench benchmark, which encompasses 16 datasets across 6 different language tasks. They reported metrics such as time to first token, TTFT speedup and accuracy, comparing LazyLLM against standard LLM inference and other baselines like random token drop and static token pruning. The results indicated that LazyLLM consistently achieved better TTFT speedup with negligible accuracy loss, exemplified by a 2.34x TTFT speedup in multi-document question answering tasks with less than 1% performance degradation. Additionally, the authors measured the percentage of prompt tokens computed and overall generation speedup, demonstrating that LazyLLM reduces total computation while maintaining performance. The analysis of cumulative token usage further supported the effectiveness of LazyLLM by showing that many tokens were never selected, indicating efficient pruning without compromising output quality.
What results were achieved with LazyLLM in terms of TTFT speedup and accuracy compared to baseline models? Can you provide specific numerical outcomes mentioned in the paper?
LazyLLM demonstrated significant improvements in time to first token, TTFT speedup, while maintaining accuracy compared to baseline models. Specifically, in the multi-document question answering task, LazyLLM achieved a TTFT speedup of 2.34 times with a negligible accuracy drop of less than 1%. Furthermore, it was able to reach a TTFT speedup of 3.0 times with only a 10% degradation in accuracy. In contrast, baseline methods exhibited a more substantial accuracy decline for similar TTFT speedup levels. Overall, LazyLLM consistently outperformed standard LLM inference and other baselines across multiple tasks, showcasing its effectiveness in enhancing inference efficiency without requiring additional training.
What are the theoretical or practical benefits of using LazyLLM over traditional methods? Specifically, how does LazyLLM improve inference speed without requiring fine-tuning?
LazyLLM offers several theoretical and practical benefits over traditional methods for improving inference speed in large language models, LLMs. Firstly, it selectively computes the key value, KV, cache for only the important tokens needed for the next token prediction, deferring the computation of less relevant tokens, which significantly reduces the time to first token, TTFT, during the pre-filling stage. This contrasts with traditional methods that often require full computation of all tokens, leading to longer TTFT. Secondly, LazyLLM employs a dynamic token pruning strategy that allows the model to choose different subsets of tokens at each generation step, enhancing performance retention while optimizing speed. Importantly, LazyLLM does not require any fine-tuning or parameter modifications, making it easy to integrate with existing transformer-based LLMs. Lastly, the introduction of an aux cache allows for efficient retrieval of pruned tokens' hidden states, ensuring that the worst-case runtime is never slower than the baseline, thus maintaining a balance between speed and accuracy.
What limitations or drawbacks does the LazyLLM method have, particularly in terms of its applicability across different tasks or potential performance degradation?
The LazyLLM method has certain limitations, particularly regarding its performance degradation and applicability across different tasks. While it allows for dynamic token pruning, excessive pruning can lead to information loss, which may degrade performance, especially if too many tokens are removed or if pruning occurs too early in the transformer layers. The empirical results indicate that as the number of pruned tokens increases, the model's performance gradually decreases, suggesting a sensitivity to the pruning strategy employed. Additionally, the effectiveness of LazyLLM may vary across different tasks, as the optimal number and location of pruning layers can differ based on the specific requirements of each task. Therefore, while LazyLLM shows promise in improving inference speed, careful tuning of its parameters is essential to maintain a balance between speed and accuracy, which may not be universally applicable across all tasks.